Okay, good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So today we will be discussing about the week six topics, which are the momentum and thermal boundary layers over a flat plate. So I will just have a brief recap about what are the contents taken in the week six. So it was a continuation from the week five topics. So in week five we were discussing about the derivation of the momentum and thermal boundary layer over a flat plate. Then in the week six, as a continuation to that, we discussed about the turbulent boundary layers mainly, and also the uh, analogy, that is the Reynolds analogy and modified Reynolds analogy, which gives a relationship between the heat transfer and the fluid friction over the flow or a flat plate. Then actually we separately consider that the flow, mainly we considered the flow is laminar, but in but flow can be turbulent also. So we studied about uh, the makes expression for turbulent when actually actually the flow is flow over a flat plate. First it used to be laminar, then there is turbulent. So in that case we have to use the mixed boundary layer or uh, mixed boundary layer conditions, where we will be considering some pop up to critical length for laminar region and then the turbulent region. So we have to use the correlation or the expressions for the same when we have a transition from laminar to turbulent boundary layer. So this was the major topics in the week three, and also uh, some of the tutorial questions were also discussed in the week six topics. So let's get started with the first question. So in this question, it's a air at 27 degrees Celsius with a free stream velocity of 10 meters per second is used to cool electronic devices mounted on a printed circuit board. Each device is 4 into 4 mm into 4 mm, dissipates 40 milliwatt, which is removed from the top surface. A turbulator is located at the leading edge of the board, causing the boundary layer to be turbulent. Estimate the surface temperature of the fourth device located 15 mm from the leading edge of the plate. So actually what happens is, in a normal condition, first up to critical length with the boundary layer will be laminar, then a transition happens. But in this case, it is clearly mentioned that we can make the flow turbulent at the leading edge itself by using some uh, techniques, like tripping the boundary line. Okay, so in these conditions it is mentioned that from the initial state itself the flow is turbulent, so there is no laminar flow at all. So this can be uh, made by using different techniques. So in this case we have to consider that the flow is entirely laminar if from the leading edge of the plate onwards. So if we draw the schematic, we have a flat plate. So air is coming at 27 degrees Celsius, and that too at 10 meter per second. And in this is a printed circuit board on which the devices are mounted. Okay. Devices are mounted like this. Okay. So the size of the device is, it is given 4 mm into 4 mm, and it dissipates a heat of 40 milliwatts. So this is our question. So we are asked to find out uh, what is the surface temperature at the fourth device, that is here. We take x like this. Okay. So we are asked to find out the surface temperature of the fourth device. So how to? So what is this? First it's already we will first the Reynolds number, that is Reynolds number is equal to u infinity x divided by mu, right? So, and this length is also given, which is around 15 mm, right? So we can replace L is equal to 15 mm. So to infinity, this 10 into 15 into 10 raised to minus 3, all divided by 17.4 into 10 raised to minus 6. So this is the expression of this is the Reynolds number. So this will comes out to be 8621. Okay, but actually we are asked to actually we are asked to find out that the flow is entirely turbulent from the beginning itself. So we need to use the turbulent boundary layer equations. Okay, so what is the expression for turbulent heat transfer at any location? The heat transfer coefficient is 0.0296. Reynolds number at x raised to 4 by 5, Prandtl number raised to 1 by 3. Okay, so Reynolds number we already found out. So h at L is equal to 15 mm is equal to 0.0296 into 8621 raised to 4 by 5 into Prandtl number is given, that is 0.705 raised to 1 by 3. Okay, so the answer to this question, so we have to multiply with x by L also. So if we multiply by with x by L, that means k by L. So that is thermal conductivity into by thermal conductivity by L. K is given as, sorry, this is 0.7. This should be 0.02704. Sorry for the mistake. So this 0.02704 by L is 0.015 into 0.0296 into 8621 raised to 4 by 5 into 0.705 raised to 1 by 3. So this is the heat transfer coefficient at the fourth at x is equal to 15 mm, or at the fourth printed circuit, or at the fourth device. So this will comes out to be around uh, 56.84 watts per meter square Kelvin. Okay, so I'm not. You can do the calculation, and if there is any mistake, you can just put it in the chat forum, discussion forum. So I will look into it if there is any calculation mistake. So this is the heat transfer, local heat transfer coefficient at this location. Okay. So next we are asked to find out the temperature, surface temperature. So we know Q by A, that is the heat flux. Okay, would be is equal to H L T surface minus T infinity. So Q is given at 40 milliwatts divided by area is also given, that is 4 mm square. So 4 into 4, that is 16 mm square, that is 10 raised to minus 6. It should be equal to H 66.84 into T surface minus T infinity is given as 27. Okay. So if we solve this, it comes out to be T surface at L is equal to 15 mm. It comes out to be 64.4 degrees Celsius. So the surface temperature of the fourth plate, no, so sorry, not the fourth plate, the fourth device, which is 15 mm from the leading edge of the body, is 64.4 degrees Celsius. Okay. So let's move on to the next question. So the next question is also based on the first question. We have to find out what is the minimum free stream velocity if the surface temperature of the fourth device is not to exceed 80 degrees Celsius. So it's just the reverse of that we did in the first question. So here our constraint is Ts is not to exceed 80 degrees Celsius. So we need to find out what is the minimum restraint velocity that we need to give to the fourth device to maintain this uh, temperature. Okay. So first, so we know Q by A is equal to just the reverse of the H X is H HL Ts minus T infinity. So this is 40 into 10 raised to minus 3 divided by 4 into 4 into 10 raised to minus 6 is equal to HL into 80 minus 27. So the HL, that is the heat transfer minimum heat transfer coefficient. So the heat transfer coefficient required to maintain this surface temperature is we can find it. So it should be around 47.17 watts per meter square Kelvin. Okay. So we know what is the turbulent heat transfer coefficient. So it is 0.0296. Reynolds number with L raised to 4 by 5 until number raised to 1 by 3. So we will get, if we substitute Reynolds number raised to 4 by 5 is equal to 47.17 divided by 0.0296 into 0.70 is the 705 5 raised to 1 by 3. So the Reynolds number it will comes out to be around 7654.8. Okay. So what is Reynolds number? Equal to u dash. I'm taking the new velocity as u dash L divided by mu. So u dash is equal to Reynolds number at L into mu divided by L. It is 7654.8 into mu is given how much? 17.4 into 10 raised to minus 6 divided by what is L.015. So if we calculate this, it will comes out to be yeah, comes out to be around 8.88 meter per second. So this is the minimum velocity that we need to supply in order to maintain the device temperature not to exceed 80 degrees Celsius. Okay, which means we should give at least 8.8 meter per second in order to restrict the increase in the device temperature beyond 80 degrees Celsius. So let's move on to the next question. So in this question, we have 100 electrical components, each dissipating around 25 watts are attached to one surface of a square of 2 meter into 2 meter copper plate, and all dissipated energy is transferred to the water in a parallel flow over the opposite surface. A pro turbulence at the leading edge acts to trick the boundary layer, and the plate itself may be assumed to be isothermal. So the water properties are given, and we are asked to find out what is the temperature of the copper plate. So, so we have one copper plate here of size 0.2 into 0.2 square plate, and on one side of it we have 100 devices. 100 devices are, this is just a representation. 100 devices are placed on one side of the plate, and over the opposite side water is flowing. Okay. Water at 2 meter per second and 17 degrees Celsius is flowing over the opposite side of the plate, and and there is a and the throw turbulence is created at the leading edge. So by tripping the boundary line. So we should assume that the flow is turbulent. Okay, the flow is turbulent. Then we need to find out what is the temperature of the core plate. So here, and he has asked to find out that the plate is isothermal. Okay, so we need to find out what is the total heat transfer from the plate. Total heat transfer from the plate. This is the 25 watts and 100 components, that is 2500 watt is the total heat transfer that is taking place from the plate. So heat flux, total heat flux is 2500 divided by 0.2 into zero point 0.2. This much watts per meter square is the heat flux uh, heat flux from the that is dissipated from the plate. So we are asked to find out the surface temperature of the plate. So here we need to find out the average heat transfer coefficient. So what is the basic definition for average heat transfer coefficient over a length L? So it is, or for any distance x over a length x, it is h bar x, that is average heat transfer coefficient is 1 by x integral 0 to x hx dx, right? So if we substitute this values 1 by x integral 0 to x k by x 0.0296. Sorry, here I forgot k by l. So here I should multiply by l by k. Okay. So what is l? It is 0.015 and k is 0.022764. So after that you will get this answer. Sorry, I forgot in the last question. So let's continue with the third question. So into Reynolds number of x raised to 4 by 5 and Prandtl number raised to 1 by 3 dx. So Reynolds number x is equal to u infinity x by mu. So if we substitute and if we do the integration and substitute, we get h bar x is equal to around 0.037. 0.037. So it will come out to be, so if you write the average heat transfer coefficient over x, it comes out to be points x by l x k by x 0.037, Reynolds number at x raised to 4 by 5, Prandtl number raised to 1 by 3. Okay, so this will be the average heat transfer coefficient over a length x in the turbulent boundary layer. Okay, so if we substitute h bar x is equal to k is given 0.620, then uh, x is given, sorry, x means we are taking the entire length, so we can write here hl. So l is 0.2, it is a square 0.03037. Knowles number we need to find out what is u infinity, that is 2 into 0.2 divided by mu is given 0.96 into 10 raised to minus 6 raised to 4 by 5 and Prandtl number is given 5.2 e raised to 1 by 3. So the answer HL, it will come out to be H bar L will come out to be around 6189.78 watt per meter square Kelvin. This is the heat transfer average heat transfer coefficient over the entire length of the plate. So now we know with the Q heat flux we know H bar L we know is T surface average surface temperature minus T infinity. So which is equal, so we can find out Ts bar is equal to Q double dot T by H bar L plus T infinity. So which will come out to be Ts bar is equal to 2500 into 0.2 into 0.2 into 6189.74 plus what is T infinity? It's 17. So the answer comes out to be around 27.1 degrees Celsius. So please check if there is any calculation mistake or not. But the way of doing this problem is correct. But there may, if mostly there won't be any calculated mistake. But if you find any calculation mistake, you can uh, intimate me in the next class. Okay. So I hope that question was clear to you. So that in that question we need to find out the average heat transfer coefficient. Okay, because the plate is assumed to be isothermal. So in this fourth question, we need to find out the it's a continuation of the third question. So we need to find out if each component has a contact surface area of 1 centimeter square. That is, uh, in the question it is said that we have a 0.2 into 0.2 square plate, and over that plate 100 components which dissipates 25 watts each is placed on the board. So, and we are asked to find out the average surface or the surface temperature of the plate. So, in this question, the each plate surface area is given and a contact resistance is also given. So, we are asked to find out what is the component temperature, what is the temperature side. That is, if this is the plate, okay, and I'm just taking one representative component only. So, this is the component. Okay. This is TS and this is the TC. Okay. We are asked to find out what is TC. We are asked to find out the temperature variation across the thickness of the copper plate. We can neglect. Okay. So this the conduction resistance across the thickness of the plate we can neglect. So the only resistance that is happening is the contact resistance. RC. Okay. So if you write this is the heat transfer network. So if you write Q double dash is equal to delta T divided by RC contact resistance divided by contact resistance of Q is equal to this is each at the area contact area, right? So this is 25 is equal to Ts minus Tc, or mostly means Tc will be higher. So Tc minus Ts divided by the contact resistance is 2 into 10 raised to minus 4 divided by 1 into 10 raised to minus 4. That is, this is centimeter. We have to convert it into meter. So okay. So this and this cancels. So Tc minus Ts is equal to 25 into 2. That is Tc minus Ts is equal to 50. So Tc is equal to 50 plus Ts. That is 50 plus 27.1. This is 77.1 degrees Celsius. So this will be the temperature of the surface temperature of the component or the component temperature. So here we are not considering that we are not considering conduction resistance across the plate. That is the plate. We are not considering that there is any conduction resistance to across the thickness of the plate and also this component across the component. Means we are just considering only the contact resistance between the this plate and the component. Okay, we are neglecting other resistances. So I hope this question was also clear to you. So let's move on to the next question. So in the question number 5, it is said that the air is flowing over a heated plate at a velocity of 50 meters per second. The local skin friction coefficient at a point on the plate is given 0.004. Estimate the local heat transfer coefficient at this point. So I hope you got means from which portion this question is taken. So it's from the Reynolds modified Reynolds analogy. So what is Reynolds analogy? According to Reynolds analogy, it's a relationship between the friction coefficient and the heat transfer. It's a frictional pressure drop and the heat transfer over a flat plate. That means if we get the frictional pressure drop or the coefficient of friction, we can find out the heat transfer at that point or vice versa. That is basically the Reynolds analogy. And there is Reynolds Colburn. For Reynolds analogy is only applicable to Prandtl number 1, where the standard number is equal to Cf by 2. That is the coefficient of friction by 2 for local skin friction coefficient by 2. But in a modified Reynolds analogy, it's applicable to a wide range of Prandtl. So, so here the Prandtl number is not equal to Prandtl, it's air, so the Prandtl number is not equal to, and so we have to take the Prandtl number means Prandtl number not equal to 1, so we have to use the modified Reynolds analogy. That is Prandtl number at any point. Prandtl number raised to 2 by 3 is equal to Cfx by 2. So this is the modified Reynolds analogy. So for that we need to first calculate the Prandtl number PR, that is equal to K divided by rho Cp. So mu by alpha. So alpha is equal to K divided by rho Cp. So K is given, how much is K? 0.035. Density is given 0.88. Cp is given. So if we calculate this, we will get otherwise, yeah, if we calculate this, we will get it in calculated it. That means 0.035 divided by. So the alpha will come out to be 0.0000397 meters per second. So 286 into 10 raised to minus 5 divided by 0.00000397. So this will be 2.286 divided by 8. Okay, so the Prandtl number will comes out to be around 0.6537. Okay, that is the Prandtl number. So next we need to find out what is standard number, that is x into 0.6537 raised to 2 by 3 0.004 by 2. So the standard number at x we will find it will comes out to be 2.6 into 10 raised to minus 3. Okay. So what is standard number? Standard number is equal to Nusselt number divided by Reynolds number into Prandtl number. What is Nusselt number? Hx by at any location x. K into u infinity x by mu into Prandtl number is mu by alpha. So this is cancelled. This is cancelled. So it becomes h alpha divided by k u infinity h by k u infinity, that is alpha. Alpha is k divided by rho cp. This is cancelled. It becomes h at x divided by rho u infinity cp. This we got it as 2.6 into 10 raised to minus 3. So we are asked to find out what is the heat transfer coefficient at the point. So h at x is equal to 2.6 into 10 raised to minus 3, 0.88 into what is u, 50 meter per second. In 1 minute, sorry, into 1.001 into 10 raised to 3. So what is this answer? 2.6 into 0.88 into 50 into, so it will come out to be the heat transfer at that point will be 11.4 watts. So actually, I think you got the importance of this Reynolds analogy. So we just need to calculate the uh, even without heat transfer, we can predict what will be the heat transfer coefficient over a flat plate. If we calculate just the uh, uh, skin friction coefficient at a surface. So even actually the heat transfer taking place, we can predict what will be the heat transfer coefficient at that point. So that is the use of Reynolds analogy. So let's go to the next question, that is consider atmospheric air at 2 meters per second at temperature 300 Kelvin in a parallel flow over an isothermal flat plate of length 1 meter, temperature 350 Kelvin. Calculate the local convection coefficient at the trailing edge without unheated starting. So till now we have what we studied is the heating starts at the leading edge itself. But in but, but in some cases heating starts from some other point from the leading edge. So say for example this case. This is a flat plate, okay, and this is the leading edge. and till this epsilon, there is no heat transfer. So what happens is the momentum boundary layer will grow from the leading ether, that is hydrodynamic boundary layer will grow from the leading edge itself, but this is T infinity. But from this onwards it is Ts. Okay. So as soon as means when after the unheated starting length, so we will say that unheated length. After this unheated length, the tem we are changing the temperature of the plate by some other means. So by giving a heat flux or um, the isothermal conditions. So the temperature between the free stream and the surface or the plate surface is different. So there will be a heat transfer. So the boundary layer, it's a thermodynamic boundary layer will start growing from here. So the momentum boundary layer has already started from the leading edge. So this is a condition known as heat transfer with unheated starting heat heated. So let this concept be here. We will come back to this later. So in this question, consider an air which is flowing at 2 meter per second and temperature 300 Kelvin in parallel flow over isothermal flat plate of length 1 meter at temperature 350 Kelvin. Consider the calculate the local convection coefficient at the trailing edge without unheated starting length. So this is our normal case where there is no unheated starting length. So eta is equal to 0. So just a normal case where the boundary layer and both thermodynamic and hydrodynamic boundary layer starts from the leading edge itself. Okay. So this is common. This is same we have done in the previous questions. So you're asked to find out the heat transfer coefficient at the trailing edge. That is h at x is equal to L. That is uh, we need to calculate what is the boundary means. First, we need to calculate whether which is laminar or turbulent because the question it is not specified. So Reynolds number at x is equal to L is u infinity L divided by mu. So what is u infinity? That is 2 meter per second. L what is the length of 1 meter? Mu is what is mu? 18.4 into 10 raised to minus 6. So this will comes up to 1.087 into 10 raised to 5, which is a lambda. So we can use the laminar heat transfer expression for laminar heat transfer coefficient. So what is x? So hx at L is equal to point. That was the point x. I always forget to put x by k by L into 0.332 into Reynolds number at L raised to 1 by 2 and L number raised to 1 by 3. So k is given how much? 0.0282 L1 into 0.332 into 1.087 10 raised to 5 raised to 1 by 2 into until number is given 0.703 raised to 1 by 3. So the answer Hx comes out to be 2.71 watts per meter square Kelvin. So this is the heat transfer coefficient at the trailing edge without starting edge. So let's go to the next question. So it's a continuation of the last question. So here we have a unheated starting length of 1 meter. So we already have 1 meter heated length. So in front of that we have a 1 meter additional 1 meter of unheated starting length. So the total plate comes out to be of 2 meter, right? So we have this is x. So we have total plate length of 2 meter, and we have a starting length of epsilon 1 meter. So the hydrodynamic boundary layer will be like this. This is hydrodynamic boundary layer, and this is thermal boundary layer. So for the in this case we have the heat transfer coefficient expression or the Nusselt number expression, which is nu at any location is equal to nu at that location nux, that is nu at that location when there is no heated length minus divided by 1 minus epsilon by x raised to 4 3 by 4 divided by raised to 1 by 3. So this is the expression for the unheated starting length. So we can get back to the means this previous expression. Yes. Say for example, let's assume if there is no unheated starting length, so epsilon will be 0, right? So this term will be 0. So nux will be equal to nux when the epsilon is equal to 0. So what is this is 0.332 Reynolds number x raised to 1 by 2, Random number raised to 1 by 3, divided by 1 minus epsilon by x 3 by 4 raised to 8. So this expression will revert back to the or go back to the previous expression for the unheated length. But here we are asked to find out the heat transfer coefficient at the trailing edge, right? Here also trailing edge. So here x is equal to or L is equal to, so at L we need to find out. So nu at L is equal to 0.332 Reynolds number L raised to 1 by 2 and a number raised to 1 by 3 divided by 1 minus epsilon by L 3 by 4 raised to 1 by 3. Here L is equal to 2 meters. So here L is equal to 2 meters. So we have to take x from the leading edge of the or the starting of the plate or where we start the means where the hydrodynamic boundary layer goes. So if you calculate NUL equal to 0.332, so Reynolds number we need to calculate, that is U infinity into, that is what is U infinity? 2 meter. 2 into 2 divided by what is nu? 18.4 to 1 by 2. What is Prandtl number? 0.703 raised to 1 by 3. That will be 1 minus epsilon is 1. Because in question it is given that it has an meter starting length of 1 meter divided by 2 raised to 3 by 4 the whole raised to 1 by 3. So the answer to this question, if you calculate, it comes out to be around 185.27. This is a Nusselt number. So what is the heat transfer coefficient? That is the question. So that is nu k by L. So 185.27 into k is how much? K it is given as 0.0282 divided by L is 2. So the answer comes out to be 185.27 0.0282 divided by is 2.61 watts per square meter. So this is the answer. So if you want to means know more about this unrated starting length, you can refer to the Incorpora textbook, chapter number, chapter name, external flow. So I don't remember the chapter number is like, chapter number 7, external flow. Okay. So here, there it's written in more detail. So I hope this session was useful to you. So thanks for watching. Thanks for listening. So we will meet in the next week with some practice problem for week 7. So hope have a nice week ahead. Thank you. Thank you very much.